Okay, so welcome back to the second part of this video on calculating the expected distance between two standard normals. Okay, so what we want to try and do is we want to work out how is this random variable going to be distributed, i.e. we're going to map this abstract probability distribution onto, again, the real line in a different way this time. This is going to be the random variable x minus y, and what we then want to do is take the modulus of that and take the expected value of the modulus of this random variable. So firstly we need to work out what this random variable is. Okay, and the way we're going to do that is we're going to use moment generating functions, because if you remember, the moment generating function of let's say just a random variable, let's just call it x for now, the moment generating function of a random variable x as a function of t was going to be equal to the expected value of e to the t x, basically. So you constructed a new random variable which was e to the t of x, where t was just some fixed parameter, but obviously the moment generating function varies with t, and then you take the expected value, but as far as the expected value is concerned you can just treat t as a constant effectively. Okay, so what we are now going to do is look at the moment generating function of x minus y as a function of t. Well, this is going to be the expected value of e to the tx minus y, in brackets like that. So we can split this up into the expected value of e to the tx times the expected value, e to the negative ty. Now, we showed using the bivariate version of the law of the unconscious statistician that providing these two are independent, which we stated x and y were going to be independent, and therefore the expected value of x and the expected value of y, I'm reading that e and saying the expected value, e to the t of x and e to the negative t of y should also be independent. The reason being that if knowing the value of x does not give me any information about the value of y, then why should knowing the value of e to the t of x give me any information about the value of e to the t of y? If it did, then knowing the value of x would give me information about the value of y. So basically, if these two weren't independent, it would contradict x and y being independent. So basically, if x and y are independent, e to the t of x and e to the negative t of y are also independent. So we can split this up into the expected value of e to the t of x times the expected value of e to the negative t of y. Okay, and I need to get onto a new piece of paper. I need to save that. Okay. Oh dear, not like that. Onto something else. Right. Okay. So we just got to the point where we had said that the moment generating function for x minus y as a function of t was equal to the expected value of e to the tx times the expected value of e to the negative ty, t big Y. Okay, well, the first thing to note is that the expected value of e to the t of x is normally distributed, x is standard normally distributed with mean 0 and 1. So this is the moment generating function for x, and the moment generating function for a standard normal we've seen in previous videos is e to the t squared over 2. Okay, so now let's look at this one here. We have to remember that y is normally distributed with mean 0 and variance 1. So what did that mean, remember again? We had this new probability space which was omega cross omega, and we were ascribing value, y was a random variable ascribing to each of these outcomes a real number, and of course it wasn't one-to-one in the slightest, because this was taking any outcome, let's say s prime, and it was only depending on what s prime was. It was taking onto x bar of s prime, basically. So no matter what your value of omega in your first position is, it was mapping you onto the same value of the real number, so it certainly wasn't one-to-one. Okay, so the thing to note, however, is that if we now take a new random variable, which is negative y, which is basically we're just going to map you onto the same number as in here, but the negative version of it. So if s prime went to, let's say, it went to 5, we're now in negative y is going to send it on to negative 5. But now you just look at the symmetry of the normal distribution. The PDF of the standard normal is perfectly symmetric around the y-axis. So when you send it to -5, what you're basically going to do is you're saying, okay, all the points that were sent onto 5 before are now being sent onto -5, so we need to send the PDF of 5, this probability density for 5 now needs to go on to -5, but it was exactly the same already. So basically all you're going to do is flip this probability density function around in the y-axis, but you'll get exactly the same thing back again. So -y basically is again just normally distributed with mean 0 and variance 1. Okay, so the moment generating function for -y, which is here, is again a standard normal distribution. So this is going to be the expected value of t squared over 2 as well. Okay, so now what we get is that the moment generating function for x minus y as a function of t is equal to e to the 2t squared over 2. Right, okay, so now what we need to do is, e to the 2t, yes, e to the 2t squared over 2, because when you multiply these two together, you add the indexes. Well, you add, sorry, the powers. Okay, so now what we need to do is work out what is this? What is this as a normal distribution? Well, let's remember this is a normal distribution. This is the moment generating function of a normal distribution, but it's no longer a standard normal distribution. So let's just remind ourselves of what the moment generating function of a general normal distribution is. So if we remember, if we want a general normal distribution from the standard normal distribution, so let's say z is standard normally distributed 0, 1, and x is generally normally distributed with mean mu and variance sigma squared, then we know that we can write x as being a function of z. So if you have a basically, if you have an abstract probability space and you can find a random variable which maps it onto the real line and is normally distributed, then basically you can take a function of this random variable, which is sigma z plus mu, and you'll map that again onto the real line, and overall this new random variable you have here, which we'll call x, it will be generally normally distributed. So basically, if you're an abstract probability space, you can find a random variable which will map it onto the standard normal distribution. You can certainly map one onto the general normal distribution. But the more important aspect of that is if you can find one mapping it onto the general normal distribution, you can almost certainly find one, well, you can certainly find one mapping it onto the standard normal distribution, and that's the process of standardization. Okay, so what were we doing? Oh yes, we wanted to work out what the moment generating function for a general normal was. Well, if we want to work out the moment generating function of the general normal, we stick it straight into the formula for the moment generating function, which is the expected value of e to the t, and then we stick in sigma z, that should have been, plus mu. So I've just stuck in what x it is there. So it should have been x, but I've said x is this function of another random variable z. So this is the expected value of e to the t omega z plus t mu. Okay, so firstly we can pull out the e to the t mu because that's just a constant effectively. What if we split this up? It's the expected value of e to the t mu times e to the t omega z. Okay, but this is just a constant, so we can pull that out of the expected value by linearity. So we get e to the t mu, and then we've got the expected value of e to the t. I'll write it out. The expected value of e to the t sigma z. But this is just the moment generating function of z evaluated at t times sigma rather than t. Okay, and we know the moment generating function of a standard normal distribution, so we can just fill this in, e to the t mu, and then we'll put in, it would be e to the t squared over 2, but now we need to put in e to the t sigma squared over 2. Okay, so we know that the moment generating function for a general normal distribution, which I'll write down here, is equal to e to the t squared sigma squared over 2 plus t mu. Right, so now look at our moment generating function up here for x minus yt. This looks quite like this. We don't have a linear term, so we can rule out this bit here, so we can cross that bit out. So we know that our mean is still going to be equal to 0, basically, that tells us. But it does look like we have a different sigma squared term from 1. So sigma squared doesn't look to be 1. Instead, sigma squared looks to be 2 here. So I'm matching the 2, dividing by 2 down there. We've got the t squared matching, but the sigma squared appears to be the 2 in the numerator there. So we seem to get that the variance is equal to 2, which tells us that the standard deviation is equal to the square root of 2. Okay, so that tells us how this new random variable x minus y is distributed. X minus y is going to be distributed normally with mean still 0, but variance this time 2. And that's the power of moment-generating functions. That would have been an awful calculation to do without moment-generating functions, but moment-generating functions have made it extremely easy. The reason it would have been they've made it really easy is that we haven't actually done the hard work. The hard work is improving that a moment-generating function is unique, basically, uniquely specifies the distribution, i.e. that if I know the moment-generating function, I instantly know that this must be distributed. I didn't basically prove this step. It's a very, very difficult proof to prove that this being the moment-generating function implies that x minus y has to be normally distributed with mean 0 and variance 2. That's where all the hard work was, and we didn't do that. We stated that as a theorem, that moment-generating functions were just as good as probability density functions, cumulative density functions. Moment-generating functions were just another way of uniquely specifying all the information of the probability distribution. Okay, so we now have that x minus y is normally distributed with mean 0 and variance 2. So that's a very useful piece of information. So we have this new random variable, so I'll draw it back again. We have this probability space, which is this our sample space cross our original sample space cross our original sample space. We have this random variable x minus y, which is mapping you onto the real numbers, and we are now told that x minus y is distributed normally with mean 0 and variance 2. So if we draw a graph, it's looking like this. A nice bell-shaped curve centered at 0 with standard deviation the square root of 2. And if we want to write out the PDF, f of x minus y, as a function of, let's say, what variable should I say? We'll just use little x, but don't read anything into that. I'm just calling this real number, this variable real number, I'm just calling it little x. Okay, so that's going to be equal to, remember the PDF of a general normal distribution is 1 over the square root of 2 pi times the standard deviation, so times the square root of 2 e to the negative x minus mu over sigma, so we get x squared over it's going to be sigma squared, which is 2, so we'll get over 4, so we get negative x squared over 4 basically. One of the halves is from the original half in the standard normal distribution PDF, and the other half comes from dividing through by sigma squared, which is 2. Okay, so that's what we have. Now what we want to do is we want to work out what the expected value of the modulus of this is equal to. Well, now basically it's just a problem in one-dimensional lotus, and that's why this is easy, because we could have done it. We could have tackled the problem of calculating this as a two-dimensional problem in with the bivariate law of the unconscious statistician. But by doing this, what we've done is we've simplified it to a problem in using the univariate law of the unconscious statistician, which is easier basically on the old integration. Okay, so if we want to take the expected value of the modulus of this random variable here, then just by the law of the unconscious statistician, this is the integral from negative infinity to infinity, the modulus of let's say little x, and that's why I wanted you to be careful with this, writing this little x here, because it looks like I've just forgotten, you know, that surely it should be the mod of x minus y. No, because little x is the variable now that takes on every single possible value of x minus y. So if really I should call this something else. I should call this t, and let this variable be little t, and let this variable be little t. Then it would look better, I think. So I'm going to do that. Because when I put that little x, it looks as though I'm just doing this one here. But little x was the variable taking all possible values that big X minus big Y could take on. So I've just renamed that variable now t, little t, so that it doesn't cause as much confusion. Okay, and then I put in the PDF of this random variable x minus y, which is 1 over the square root of 2 pi times the square root of 2, e to the negative t squared over 4, and then we obviously have to integrate dt. But you will notice that this function is completely even. If I multiply by the modulus of t and this here, this function is even, meaning that it's symmetrical in the y-axis. But the modulus of t is also even, because if I draw that, it's this. So when I multiply this by this, I'm still going to get a function that is symmetrical in the y-axis. So basically, I can just say that this is the integral from 0 to infinity of the modulus of t, 1 over the square root of 2 pi, the square root of 2, e to the negative t squared over 4 dt, and then I can just take that and times it by 2, because the integral on one side, the area under the curve on one side, is going to be exactly the same as the area of the curve on the other side. So that's a nice thing. And the ingenious of this is now that t is always positive, so the modulus of t is just going to be t, and that's very nice indeed. Okay, so firstly let's pull some things out. You see, if I alter this stuff here, the 1 over the square root of 2 pi and the 1 over the square root of 2 cancel, and what I'm going to get is that that will become 1 over 2 times the square root of pi, because the square root of 2 here and the square root of 2 within the square root of 2 pi are going to go together and make 2. But that 2 then cancels with the 2 that we've got here, so those two can cancel and we just get 1 over the square root of pi. The integral of 0 to infinity t times e to the negative t squared over 4 dt, basically. Okay, so now that isn't a too challenging integral, and the reason is that if we consider what the derivative, let's say what is the derivative of e to the negative t squared over 4, if we consider what that is, then by the chain rule it's going to be e to the negative t squared over 4 times the derivative of the thing inside, which is just going to give us negative 2t when I differentiate rather the t squared over 4. So I'm going to get this is equal to negative t over 2 e to the negative t squared over 4, and that looks very similar to the thing here. So this thing here is going to have an antiderivative very similar to here. So if I just make a few little alterations, if I say let's instead look at the derivative with respect to time, with respect to this variable t, of negative 2 e to the negative t squared over 4. You see, I want it to cancel. I want it to cancel this negative sign. That's useless. I don't want that. And I want it also to cancel this division by 2. So if I now look at what the derivative of this is, then the negative 2 e to the negative t squared over 4 by, that's just the derivative of the exponential. Now we take the derivative of the inside thing and we get negative 2t over 4. And now that cancels down to just give us t e to the negative t squared over 4. So the antiderivative of t e to the negative t squared over 4 is this thing here, negative 2 e to the negative t squared over 4. So by the second fundamental theorem of calculus, this integral is equal to 1 over the square root of pi from the front, times the antiderivative of this evaluated at infinity, which we'll have to do a limit obviously. So let's put the limit as n approaches infinity of n e to the negative, oh no, sorry, that's not the antiderivative. The antiderivative is this thing here, negative 2 e to the negative n squared over 4, minus the antiderivative evaluated at 0, so minus 2 e to the negative 0 squared over 4. Okay, so if we evaluate that, this limit, as you make n go to infinity, we're taking, if you look at this graph, we're taking the limit of this function effectively as it goes to infinity. What we're really doing, of course, we've got this negative sign out the front, so the thing we're really taking the limit of is something that looks more like this. But as you go to infinity, it's just going to go to 0, so that's 0. And then on here, we've got 2, because the negative cancels with the negative, and then we've got times 1, so we get 2 overall. So the overall answer we get is 2 over the square root of pi. So there you have it. There is the expected distance between two standard normal distributions. So basically, if you have two people picking values, picking real numbers if you like, and the chance of them getting a certain real number is distributed normally, standard normally, then the expected distance between them is going to be 2 over the square root of pi.